So today I'm going to give a talk on this Jet scheme of monomial ideal. And the final result is that we will be able to write down the irreducible components of Jet scheme over a affine scheme, over a monomial scheme, sorry. So first I'll give a revision on the Jet scheme. So first. So first, I will give a general definition for Jet scheme, and then we will just focus on the affine scheme and K points of that scheme. To start with, we let K be we let X be a K scheme of finite type. So finite type here mean X can be covered by a finite number of affine scheme, and each of them has coordinate ring finite generated K algebra. M is a non-negative integer. Then this definition describes the functorial functor points of this Jet scheme. A scheme of finite type K, a scheme finite type over K is the mth Jet scheme of X, denoted by this if it satisfies the following property. So for every K algebra A, there is a bijection from this set to this set. And moreover, this bijection is functorial in A. So this, in order for this definition to make sense, we need to show this J and this Jet scheme exists. If it exists, then it's unique up to a canonical isomorphism, and we have to construct it to show it exists. I'll give some remark on this. If the Jet scheme exists, then we can show it is unique up to a canonical isomorphism. And this follows from the Unida lemma. Now the second comment is that I'll give a kind of very quick sketch how to construct this thing. So first, to show this jet scheme exists, because X is finite type, we can cover it by affine scheme, where each of these UI is spec of some finite generated K-algebra. We can construct check scheme of UI for each of these affine cover. Then we glue them together to get a then you can show that it's, by this definition, it satisfies the property, the defining property in the previous definition. All right, I won't spend time on proving this rigorously, and you can do this. It's not hard, and the key idea will be encoded in the special case we care about. So now on this talk, we will focus on the following case. Where X is a affine.
I think you need to move the orb cam over, Zhongtian.
Oh, yeah.
Cool.
We'll focus on this special case. Where I is the ideal generated by the following polynomial.
If you don't mind me just inserting some high-level intuition for people to help them follow along. So the jet scheme of X is telling us about points and tangent vectors and sort of the next thing in the Taylor series expansion beyond tangent vectors and so on. And to understand its geometry is basically to understand the possible ways of moving through the points of X, and sort of the form of those set of ways is the geometry of the jet schemes and the arc scheme. So in the case of SLT, you could think of X, for example, as being the set of true parameters. And we know that's an extended object. And if you think about, for example, the learning process, whether it's SGD or something else that's attempting to find points of the set of true parameters, and once it's found them, perhaps moving along the set of true parameters, or maybe we're imagining a process like SGD that is never quite on the set of true parameters but is nearby, and you could project the motion onto the set of true parameters. And then sort of think about, well, what does the learning process do? In what way does it move along the set of true parameters? And which of those kinds of motions is, in some sense, more probable? And that seems likely to be related to the geometry of the jet scheme of the set of true parameters. So just to set the stage a little, that's sort of where this is motivated from in terms of SLT.
Thanks, Daniel, for the comment. Then I'll proceed. So now we focus on this affine scheme, and from our definition we can see, like, well, first of all, what is the set of MJets? So from the definition, we know this. And this will induce the K-algebra the set of K-algebra homomorphism. Right, so this will be the set of MJets. Now let's have a look at to give it a geometric structure or a structure of variety. Let's construct the defining equations. So let's have a look at what one jet looks like. A one jet will looks what a M jet looks like. An M jet is a K-algebra homomorphism. Say phi from here to here. Such a homomorphism is determined by the image of each of these generator X. Phi is determined by the image of xi. So x1 will map to a polynomial in T with coefficient in K. I'll use this notation. Then in order for phi to be well-defined, we need to map the whole the ideal I to 0. So in order for phi to be well-defined, we need the following to be true. So each of this generator will map to 0. Equals 0 in this ring. For all I equal 1 to R. Right. So if you just write down what does this polynomial look like, this will be a polynomial. This will be a polynomial in T with coefficient polynomials in this X, this capital X. So let's write this as the following. You just span this and collect terms. So where each of these f I j is a polynomial in all this capital X. Then we're able to give the set J and X a structure of variety. So the set of MJs is cut off by all these polynomials. I'll use this notation. U goes from 1 to n, and V goes from 0 to m. Quotient out this ideal. Yeah, and we will use this to denote this ideal. Any questions so far? Okay, so this is a definition of jet schemes. Now the question we want to ask is, what can be said about the ideal when I is a monomial ideal? Now let's look at an example. Let X be this affine scheme. Yeah, so this corresponds to this course. This is the picture. Now let's compute the first jets of this variety. Let's compute So by definition, one jets will be a K-algebra homomorphism from here to this ring. So this is determined by where we send x and y to. So x goes to x0 plus x1t, y will goes to y0 plus y1t. And in order for it to be well defined, this product xy has to be 0 in this ring. This will be x0 plus x1t. Now we collect terms. For constant term, we'll get this. For degree 1 term, we will have x0 times y1 plus x1 times y0t. And the higher order term just vanish in this ideal, in this ring. So now so in order for gamma sits inside first jet scheme of x, we need x0, y0 equals 0, and x0, y1 plus x1, y0 equals 0. So these two are the defining equation for one jets. So the ideal is given by this. And this is the ideal in polynomial ring in 4 variable. Yeah, and we notice that this, even though I is a monomial ideal, but this Ji is no longer a monomial ideal. But let's have a look at what is the irreducible components of this first jet scheme. Let's compute the irreducible component of J1x. And we will notice that this is same as we compute the minimum prime ideals over J1i. Yeah, for these two things to be equivalent, we have to be careful since we don't require that K to be algebraically closed. So maybe I'll just make a remark here. If K, say if K is not algebraically closed, say just K is real number, how do we say these two? How do we compute the irreducible components of a variety? So let X be a algebraic set in, say, Rn. And we know X can be written as a union of irreducible components, and this is unique up to the ordering. Irreducible. Then for each of these irreducible sets, we know algebraic set, we know that their corresponding ideal are minimum primes over the corresponding ideal of X. But if we just start with this ideal Ix and we compute all the minimum prime ideal over Ix, the irreducible components of X only correspond to a subset of all such minimum prime ideals. So this is as R is not algebraically closed. Not all minimum primes over Ix gives irreducible components of X. So what we should do is we compute all the minimum primes over Ix and check one by one, say which one gives a irreducible algebraic set, and this will be the irreducible components of X. So to find irreducible components of X, we first compute minimum primes over Ix. Say we compute all of them, then irreducible components of X corresponds to Pi, where the vanishing set is irreducible. Does this make sense? Right, let's get back to the example. Now let's just compute all irreducible primes of this ideal. So now we know the ideal is this. To compute its irreducible primes, let's see. So let P be a irreducible to compute the minimum primes. Let's let P be a minimum prime. Of I, then so it's a minimum prime ideal over I over this J1I. It has to contain these elements, right? If it contains this product as a prime ideal, we know there are two possibilities. Either X naught is in the prime ideal or Y naught is in the prime ideal. Let's look at first case. If X naught is in the prime ideal, then from this generator, we know that X naught, Y naught is in P. And this sum is in P tells us that X1, Y naught is in P as well. Oh. And again, because this is a prime ideal, we know either X1 is in P or Y naught is in P. Then we do the same thing for the second case. So Y naught is in P means that X1 times Y naught is in P, which tells us is X naught times Y1 is in P. Then this tells us either X naught is in P or Y1 is in P. Now we'll be able to write down the irreducible primes. Should we move to another set of boards?
Yep, let's do that.
Right, so from our calculation, we can conclude that these are all the irreducible primes. And each of these prime ideal corresponds to give us a irreducible algebraic set. So these are all irreducible components. Then we notice that in this case, the irreducible components are all monomial and with ideal given by this. And this is not just for this case. Actually, this holds for this example can be generalized for all monomial ideals. So the theorem is that I be a monomial ideal then each irreducible components of J and I is a monomial scheme. Now we start to prove this theorem. Before we prove the theorem, let's introduce the following lemma to reduce the case to where I is a principal ideal. So we can reduce to the case of hypersurface. The lemma is let I and J be ideal in this polynomial ring. And suppose minimum ideal minimum primes of I and J are of forms 1 x. So let's I and J be two ideals in this polynomial ring, and we suppose their minimal prime ideals are all of this form. So it's generated by each of these x, generated by some subset of the x. Then minimum primes of this ideal are minimum elements in the following collection. P is a minimum primes of P, minimum prime over I, and Q is a minimum prime over J. Does the statement make sense? No, any question for this statement? Like,
I think it's fine. It's if you have the background to understand it, you probably understand it, and otherwise, there's not much we can do right now. So you might as well continue, I think.
right. Yeah. If you try to prove this, you will say it's not hard. So this lemma tells us that we can just focus on the hypersurface. So consider I be the ideal generated by the single monomial. Where each of you I is non-negative integer. Now let's restate the previous theorem with more details. So now let I be this ideal. Then the minimum primes of the ideal of MZ are precisely the minimal members of the following set. That's P. where each of these AI is an integer greater than equal to -1, less than equal to m, and we have this inequality. So here, this -1, if say a1 equal -1, just mean this term just do not appear in this ideal, in the generator. Right, and by minimum here, I mean minimum with respect to the following order. So the order on P is given by take two ideal in this collection. So they are indexed by this AIs. This one is smaller than this one. If and only if each AI is less than or equal to BI. Any question? Does the statement of phase theory make sense? Cool, let's prove this theorem. Yeah, the proof is actually quite easy. So the idea is that we want to decompose.
Sorry, maybe this is a stupid question, but why isn't this just ideal containment?
Yeah, I think that gives the same order, right?
Mm-hmm. Okay, so you're saying it in order to make clear that this is a very simple order.
Yeah. Yes.
Mm-hmm.
Yes. Yeah. So the idea is, we want to decompose the MJs of the affine space into irreducible components, irreducible closed subsets, and show some of these irreducible closed subsets are irreducible components of the MJs over X. Okay, let's start. First, let's consider an MJ over the affine space AN. An MJ over AM by definition is a K-algebra homomorphism. say gamma from the polynomial ring to this ring. So this is completely determined by where we send this variable to. Now let's define some number to this. Let's define a number associated to this mz gamma. Define a tuple denoted by a gamma where each of this AI is a number in this set. So let's first for I in this set with xi0 is non-zero. We set ai equal -1. Otherwise, define ai to be the maximum number with the property that xij equals 0 for all j greater than 1 less than equal to ai. Yeah, so this is just saying that, okay, we start with one mjs over the affine space, which is determined by this, which is determined by the image of this xi, right? So for each I, let's first look at, let's find the terms, say here, x1, a1. This a1 will be the number so that all terms before this term are 0. And we take the maximum one, which means the next term, x1, a1 plus 1, will be non-zero. Does this make sense? So for each I, we can get a number ai. Now this is, so for each gamma in the mjs over affine space, we can associate it a tuple of number, a gamma. again, in order for this mjets over affine space lies be an mjets over X, we need the following equation. Gamma x1 u1 x and un equals 0 in this ring. Let's spell out what's this image. Yeah, because all terms before a1 plus 1 are vanishing, so we just erase them. So we start from degree a1 plus 1 terms. Let's consider two cases. First, if ai equal to n for some I, then we know ai plus 1 equal n plus 1. Then we know that this is just 0. And in this case, this is true. Yeah, this is just simply because one of this, in this case, it's just mean one of this xi goes to 0. So then the whole thing has to go to 0. So this case is trivial. Now we look at the case that if for all I, ai is less than n, then let's compute the lowest degree term of, I'll just rewrite it here, of this product. So the lowest degree term of this is given by this expression. So we just take the lowest degree term in each of this term and multiply them together. We will get the lowest product for the whole, lowest term for the whole product. Yeah, remember we have the exponential here. Does this make sense? Yeah, and because this is just a single term, there's no cancellation. And in order for the product to be zero in this ring, then the degree of this has to be greater than greater than equal to n plus 1, right? If the degree of this is less than n plus 1, then this is non-zero, because the way we choose AI makes all this coefficient non-zero. So in order for this thing to be zero, then the degree has to be greater than equal to n plus 1. So since the coefficient is non-zero, by the way we choose this AI, we know the degree of this term, which is this, has to be greater than equal to n plus 1. Does this make sense? Then combining these two cases, we conclude that for gamma to be a mjets over x, we have to have this inequality. Right? So if gamma is an mjets over x, we just show that this has to be true. And if this is true, which means the product here, will have the least degree of this polynomial will be greater than n plus 1, which is 0 in this ring. Yeah, so what we have done is that for each mjets over the affine space, we associate a tuple number, and in order for then we get a characterization of mjets over x. So for this gamma to be an mjets over x, we need this inequality. And so now let's write that down. So for each tuple here, let's define this set. This will be the mjets over the affine space An, so that the associated tuple to gamma is given by this A. right? For each gamma, we can attach a gamma to it, and say A will just be a collection of gamma, so that this A gamma is equal to this particular tuple. Then we notice the following fact. First, the MJs over the affine space is a union of all these CAs. Right, this is just follow from definition. And second of all, we notice that each of these CA is a vanishing set of the following ideal. This just follow from the definition of this or this A gamma. And because this is a prime ideal, we know it, which is irreducible. The third thing we want to mention is that if we have two tuples and A is less than B, this means AI is less than or equal to BI for all I. Then say B is a subset of say A. Yeah, this just follow from the definition of this CA. If A is less than B, then the defining ideal for CA is contained in the defining ideal for CB, hence CB is contained in CA. Any questions so far for these three conclusions we made?
Silly question. In your notation there, where you say for C, A is gamma in the jet scheme, given that, what is A sub gamma? If not A?
Oh, this.
I guess I don't.
Yeah, it's like here. Let's get back to here. Here we start with a MJs over the affine space. Then we associate that gamma a tuple, and where this tuple is, and this tuple is defined this way. So for each gamma, we can associate a tuple. Yeah.
Yep. Awesome. Thank you.
Then we just group all this gamma according to this tuple.
Cool. Thanks.
Yeah. Any other questions? Yeah, now we finished decompose the MJ scheme over the affine space into this irreducible components. And we'll also show that some of them is contained in the jet scheme over X. Our discussion. What shows that Yeah, this is follows from the discussion we had here. Yeah, here. But for each gamma, we associate a tuple, and we also deduce a characterization of mjets over x in terms of this tuple, which is this equation, this inequality. And also we have this ordering here. So taking minimum a's among this set, we obtain an irreducible decomposition of mj scheme over x. Then we're done. Any question about this proof?
Maybe you could comment on how you arrived at this. So we were looking at this paper, right? It was who were the authors?
Let me check. Russell and Karen.
Yeah, Karen Smith and.
Yeah, we're looking at this paper.
Who was the other one?
Russell Gould.
Right. I forget the title. What was it? Just jet schemes of monomial ideals.
The jet scheme of monomial scheme. The jet scheme of monomial schemes.
Yeah, maybe you can correct me if I'm wrong here, but so Zhongtian was looking at this, and then there's a proof, and then there's a remark at the very end of the paper, which actually basically contains an alternative argument to the rest of the paper, which is much more straightforward, and which seemed a bit cryptic, and then Zhongtian thought about it more, and that's the argument he's just given, which is more straightforward than what they did. So in some sense, this is the right way to think about computing the jet scheme of monomial ideals, which is, I would say, kind of an exercise. Is that an accurate description?
Yes. Like the whole paper, the paper is quite short, and the whole paper is trying to prove this theorem. And they use induction and split into several cases, use induction to prove this. But in the end, there is a remark, just half a page, which basically this argument here.
Yep.
Yeah. So, right, this. Yeah, so, no question about this proof. Then let's have a look at some consequences of this theorem. So if the monomial ideal we start with is a reduced monomial ideal, which means it is a vanishing set of this monomial. So all exponents is just one.
Sorry to interrupt again,
if
Zhongtian, but
X
maybe
is
it's worth pointing out that the reason we even Googled for this term, jet scheme of monomial ideals, is that, well, we know that at least once we take the resolution, we can put the kinds of singular varieties that we care about locally into the form of monomials, u to the 2k equals 0. So computing the jet scheme of that is not the same as computing the jet scheme of the original thing, but it's kind of a reasonable thing to play with to start. So that's why we were doing this exercise.
Yes. Right. So if X is a reduced monomial scheme, then from our theorem, we know the minimum primes of the jet scheme are exactly primes of the following form. Where again this AI is greater than -1 less than n, and before for any monomial scheme, the inequality we have is this. Mu I times AI plus 1 greater than equal to n plus 1. But in this case, all this ui just 1, so we will get a equality here. So the sum of I will equal to we'll just get equality here. Then we can compute the dimension of each irreducible components of the jet scheme. Then the dimension of each irreducible components of the jet scheme over X is equal to this number. This follows from that. In this case, we know all the prime ideals, they have the same height, right? Like the number of generator here is given by n plus 1, given by this summation here. Then the dimension of the variety will be the dimension of the affine space minus this height, which is this number. So in this case, this M jets is equal dimensional, which means that each irreducible component has the same dimension. Right, then, oops. Should we move to another set of board?
Yep. Maybe you could give some intuition, maybe that's what you're about to do, but maybe you could give some intuition for what these different components, or in what way are they different, and like in terms of the jet.
Okay,
Oops.
can you elaborate a little more? I didn't get
Oh,
the.
yeah, I guess it's just, I mean, you've described the minimal primes, but I think, and in your
Yeah.
head, it's immediate how these equations translate into like the vanishing of the jet to a certain order or whatever. But I think it's not automatic for everybody in this audience what the significance is in terms of the like a little arc going through the point, what these equations mean. I mean, if it doesn't seem worthwhile to explain that, then don't feel obliged to. But uh, I mean, maybe even in the example where I don't know if n was your number of variables, so x1, x2, the vanishing set
Yeah.
of that. So that's the union of the coordinate axes, and then the
Yeah.
the larger you make m, if you so there was an equation, I think it was what, sum I equals 1 to n of ai plus 1 is equal to m plus 1, is that right?
Yeah. Yeah.
Yep. Okay, so the larger m gets, then so the sum of the AIs has to be getting larger, which is saying the jets vanish to a higher degree, or one of them, maybe you keep one of them to a low vanishing order and the other one needs to keep increasing, whatever. So there's the different ways of having a jet at a given point, in this case, come from choosing the way of allocating. You've got a total degree of vanishing, like a budget for how much the sort of Taylor series expansion of the coordinates of your jet. So think about you've got the union of the two coordinate axes, and you've got at some point on that union a little smooth path going through that point, which is going along the coordinate axes. So it's a path in the zero set, in the variety. And if you Taylor expand its x and y coordinates, think of that part as a function of time, then the possible ways of passing through this point, if you think of those as being the irreducible components of the jet scheme of that order, the possible ways are classified by saying how you allocate, so a given degree of vanishing, say m, so the mth jet scheme, the ways of traversing that point according to this classification is a way of choosing how to allocate that order of vanishing between the x and y components of the jet.
Right.
Would you agree with that description?
Yes. Yes. Yeah. Yeah. I never thought about that, but that makes sense. Yeah.
Yeah.
Right. Yeah. Okay. Yeah. We just show that for the reduced monomial scheme, the jet scheme is equal dimensional, and also we know what we can compute the number of irreducible components. So the number of irreducible components or number of minimal primes is equal to the number of ways choosing R integers from this set with sum being n plus 1 minus R, which is the number of ways choosing R integers from this set with sum being n plus 1, which is equal to coefficient of this term in this product. And this is equal to the coefficient of this term in this, and using generalized binomial coefficient, we can write this as this. So then the coefficient will just be n plus r, choose n plus 1. Okay, yeah, that's all about the reduced one, but for the non-reduced one, it is not equal dimension in general. Let's look at one example. For I equal to this monomial ideal. So in this case, n equal 2, and the exponential the u equal to this tuple. So by our theorem, computing irreducible components of MJ scheme is the same as finding minimum pair, so that 2 times A1 plus 1 times A2 greater than n plus 1. Then we can draw this lattice. Right, now let's say for one jet, which is m equal to 1, so this equation become 2A1 plus A2 greater than equal to 2. This is A2, let this be A2 direction, A1 direction. A2 is greater than equal to minus 2A1 plus 2, so we can draw this line. And we want to choose a minimum tuple, so we want to choose minimum A1, A2, which will be this one and this one, right? Then the irreducible components is, in this case, will be, so we have a two choice. One is 0, 2, and the other one is 1, 0. Then we can write down the minimum primes, which will be y0, y1, and x0. We can do this for any m, right? Let me just do this. The third jet scheme. Again, the same thing, we form this lattice. And when m equal to 3, we have this equation, 2 times A1 plus A3 greater than equal to 4. Then A2. Then A2 is greater than equal to minus times A1 plus 4. Then we can draw this curve, draw this line. And now we want to pick the minimum one, which will be this one, and this one. Then we can write down the corresponding. So this 3 tuple will be 0, 4, 1, 2, and 2, 0. Then we can write down the minimum primes, which will be y0, y1, y2, y3, x0, y0, y1, x0, x1. Yeah, as you can see, with this theorem, it's very easy to write down the irreducible components of MJets over a monomial scheme. I think I'll stop here.
Great. Thanks, Zhongtian.
Any questions?